okay.
Oh, yeah,
See
I'm still in the
something.
telescope.
Oh, that's
So
so neat.
you can see the big dish from the window there.
Yes.
And then now I'm mirrored, so it's a bit difficult to point. So there we have all the equipment where the signals are coming in.
Oh,
And there are the two computers. One is for the controlling the telescope, the other one for all the signal processing. And that's, yeah, the rest is just uh, the observation room. But I can't really move because I'm wired up here. So there's no Wi-Fi, obviously, here.
wow, that's a really, really great
And
view.
oh yeah,
Thank
and you can see the thing through the roof, but
Oh,
it's
cool.
mirroring now. Yeah.
Neat. Oh, fantastic. Thank you so much. That really helps. I th well, most of us have seen the images from far away looking at the dish to see the structure, but seeing it from pretty much right underneath is uh, special.
Yeah, no, it's very comfortable here. I just had dinner and yeah, it's a it's a nice experience. If you're ever in the area, please visit us.
Oh, very
The
good.
whole building moves with the telescope, so it's an experience you will never have anywhere else.
Okay, that's different. Very neat. All right, so we should probably go ahead and get started. I think that we'll get a few folks here coming in the next couple of minutes. But we'll go ahead and begin. And this is Open Research Institutes. This is our a meeting about FPGA based work. And what we do is we talk about what we have done in the recent past, what we have planned to do coming up in the near future. And if we have any roadblocks, then we bring them up at this meeting, or if we need any resources. And what we usually do is a roundtable. What we do is open source digital radio work, primarily on the amateur bands, and we also do regulatory work to help the amateur radio, both terrestrial and space services, to make things easier for folks to take full advantage of this amazing opportunity to use the bands for all sorts of wonderful things. So what we'll do is we'll start our roundtable off with Aaron. So please let us know how it's going and what you need.
Sure. Thanks, Michelle. First of all, I want to apologize upfront because I'm the biggest squirrel of the project. If I see something, I go squirrel. So a couple of months ago, in one of our past meetings, Matthew mentioned that he purchased Pluto SDR-like radios from overseas. And after a little research, one of the models turned out to be named Libre SDR. So I decided to purchase a couple, and last week the first one arrived. Shipping took a while. It was like 2 months, and it's been a roller coaster with the tariffs and on and off the de minimis exemption. But and I even got one of the shipping messages saying that it had been confiscated by the Customs and Border Patrol. I had read on a subreddit for HackRF that they had a similar experience, that the devices were classified as RF jammers, but these are software-defined radios. Um, while I was waiting, interestingly enough, came across an ORI contributor, F50EO, Evereast, had also been working with these devices. So these radios have the Zinc 7020 on them, so they're a little bit bigger than the Pluto SDR. And in addition to the USB interface, they have a gigabit Ethernet attached to the processing system, which provides faster throughput, an SD card interface, a built-in JTAG interface. But what intrigued me the most was the 89363 clocking interface, which has a voltage controlled, temperature controlled crystal oscillator attached to a DAC with clocking signals to the FPGA. The schematic that I found on GitHub showed that the DAC being populated is 8 bits, but which is not precise enough for what we're trying to do here. But after inspecting the PCB, they did populate it with something wider, 12-bit DAC, which should be usable. And this configuration matches the Edis B200 series. So there is already available IP from Edis that can take in either a PPS, a pulse per second from a GPS device, or a 10 megahertz reference to synchronize the 40 megahertz clock feeding the transceiver. So in the last week, I created an OpenCPI system support project to support this platform. And and have been successful in executing the HDL FSK modem reference application on the platform. So in addition to the Libre SDR, I was also made aware recently of another platform called the Ant SDR E200. These are a little bit more expensive, but they are readily available at electronics distributors such as Mouser. So that ships from here in the United States and arrived very promptly. The difference here is the architecture is slightly different when it comes to the interface. The gigabit interface, instead of being attached to the programmable logic, the PL, it's attached for this platform. It's attached to the PL instead of the PS. So I've been debugging a custom Vivado project where it passes the PHY, the interface from the PL side to utilize the MAC on the PS side using what's called the EMIO for the PL. So it's been a lot of Petalinux and device tree manipulation, but I haven't been able to get working yet. I haven't found the right combination. But in OpenCPI, we do support a gigabit Ethernet interface from strictly the PL side without even interfacing with the ARM, the processing system. So that's what I may try next. But for this platform, it's the way it's built. It doesn't have accessible JTAG interface like the other one, the Libre SDR. So I'll have to open up the case and get access to it, which we are accustomed to do in here anyway. So this got me wondering a little bit, like, why are these devices have become so ubiquitous and readily available? And what would it take, if we wanted to build a custom one in the future? So I found out that on JL PCB that these are kind of these pieces like the FPGA and the transceiver are kind of common stock now, and they're available inexpensively. The 7020 for $30 and the 89363 for $45. And they also have stock of the 89371 and the ADRV 9009 transceivers. So when we get to the stage in this project that those are common parts now that we can build a custom PCB if need be. So that's what I've been working on in that. But like I mentioned earlier about being a squirrel, on another topic, I ran across a blog post by Daniel Esteves, what he posted back in 2002. And you guys might already know this and been aware of it, but he demos an end-to-end DVB-S2 GSC, both transmit and receive. So he uses the GR DVB GSE out of tree module as a transmitter, and he uses a British Amateur Television Club mini tuner as the receiver. And it turns out this chip in the tuner supports GSC, and he goes through in his post and describes on how he gets IP traffic one way only using this device. Since then, it's been 2 years. The mini tuner has been replaced by something called the Pico tuner, which uses the PiPico for the USB interface. It's a lot cheaper to get a hold of versus the FTDI chip that they used previously. So I ordered the tuner and a bunch of parts on the PCB from the British Amateur Television Club, and I plan on trying to replicate that same experiment to get end-to-end GSC, which is probably something you guys have already done at ORI. But I'm one of those that learns by actually doing. So I plan on trying to replicating that same thing on my side. So just a small thing that I noticed from the schematics between the mini tuner and the Pico tuner is that the mini tuner utilizes a parallel interface, and the Pico tuner only uses like a kind of serial interface. But I'm sure it should work the same. So I might run into an issue when I try to get that end-to-end as well replicated here. But the idea is that once I have a good understanding and test setup using the GNU radio and the receiver, that I can start implementing the ORI encoder on the FPGA to try to get that into a similar state where it becomes like a reproducible end-to-end example for that. So what I plan on the next time, since I'm still waiting for those parts, is to continue building out this system support project for the Libre SDR, because I have it working. I have the processing system up and running, and I have it running applications. But one of the things that first interested me was the fact that it has the DAC and the PPS input, so that you don't have to have lab grade equipment to do 10 megahertz reference or to feed the 89361. Because one of the things that not only for the MSK receiver, but when you try to do device to device, it makes it a lot simpler when you have the same clocks. And I'm sure we're going to hear a little bit more about that soon in this video call. But that's what I've been working on.
Post. Okay, so yes, there's quite a bit of what we've been doing with both Evereast and Dr. Estefez, and so we're familiar with the work and some of the published work in GNU radios because of our efforts. So we're familiar with the mini tuner and Evereast as a participant and contributor, and Dr. Estefez has been wonderful. We actively use several things from him, including Maya. So yeah, just a strong, appreciative vibe here, and thanks for all of this update. I think it will work out. That's my instinct and opinion. Is there anything that you might need or any resources that you don't currently have in order to keep working?
No, I don't know. There's plenty of work here, and like I said, like I keep switching back and forth, and
No, I know what you mean by that.
Yeah.
There's it's such a golden age for this sort of work, and there's literally way more. There's just so much going on, and it's all delightful. So
Yeah.
I can only enthusiastically agree with your conundrum.
Yeah, no.
No, I mean
Yeah.
it's not necessarily a distraction. I mean the things you're talking about
Yeah.
doing are directly they're relatable and important to getting things done and to producing some really good designs. So I'd just keep at it.
Okay, thanks.
Okay, let's go ahead. I'll check in with Paul and see if you have anything to update. I think the things you've been working on are directly related to some progress on Opulent Voice, and that Matthew has some progress to report there as well. So let's talk about that.
Okie dokie. As you know, our question has been why we're having difficulty getting the separate receiver to receive the MSK transmission from the separate transmitter, both being Plutos running basically the same code. We set up a configuration recently. I think we've already talked about this, where both Plutos are being fed by the same clock source, reference clock. So there should be no frequency error, no timing error, except possibly an initialization. And that has worked at some gains. We did some tests where we scanned across the entire uh, range of possible gains in big jumps, in factors of two, because it was easy, because it's a bit shift on a Mantissa. So I configured the code so that it would go by bit shifts. And we've looked everywhere, and we found two islands of sort of operation. There could be more that are smaller that didn't pick up on that factors of two search, and there could also be some that we just missed because we only really have one attempt at each gain. But in the island toward the high end of the gain range, although not as high as our theory had predicted, um, we got very weird behavior where it was getting 0-bit error rate out of the pseudo-random number generator test, but it was counting too many bits per time interval, like by a factor of 20, like a million bits per second on a system that's only 54 bits per second at the design level. So we don't understand how that could have happened. But continuing the test down to smaller gains, we found another island of gain, bigger than the one we had been working with before, that generated the right number of bits per test and also gave 0-bit error rate. Now, we hadn't done a really complete search. We may have to go back and make this search much more thorough and look for gains that work better. And by the way, these are gains only in the proportional side with integral gains turned to zero. But I decided to leap ahead in optimism. So we nailed the gain down in the middle of that lower island where it was getting the right number of bits and started running some tests. Um, and we found pretty good, reliable, not perfect, but reliable, pretty good performance out of the separate receiver. So that's a major milestone. We are able to actually generate 0-bit error rates with the right number of bits on a receiver that's not actually in the same Pluto as the transmitter. Um, Now the question is why. Um, why does that test show the tracking loops trying to pull the frequency off when we know that the frequency is not off? And in pursuit of that, just this morning, I borrowed some more equipment to the remote lab. We have a fancy Fluke signal generator that we have on loan from the local microwave ham radio group. And so now I have a separate GPS controlled uh, clock reference driving the two transmit and receive Plutos. Um, so I can start for now. I've been setting them both to exactly the nominal value of the reference clock is 40 megahertz, and that gave the same results as having the same clock, which is reassuring. And the next thing is to try some other variations, including dialing in some frequency error and see what happens. And we also need to dial back in the integral gain. So there are more experiments to do. Um, we may converge on something that works, or we may just gather some clues to figure out what explains the weird behaviors. Hopefully both. And so progress is being made in little tiny baby steps by ex extracting reality from from the experiments.
Yeah, I'm really excited to see that the Pluto independent Pluto receiver, and, we can achieve 0-bit error rate on that, which is something that, had been a mystery why we hadn't previously. So that's really exciting. The one thing that still kind of sticks with me, I think Paul mentioned it, even with the external clocks, we were seeing a frequency offset, at least in terms of the NCO adjust signal being non-zero or average non-zero, which would be indicative of a frequency offset where, so if we're using the same reference clock for both Plutos, you wouldn't expect to see the receiver having a frequency offset. So that's kind of an open question. I think there were 2 or 3. I'd thrown them in the chat. But regardless, I think was with the 2 SIGGEN setup, Paul, did we have any frequency error on the receiving Pluto? I think it didn't, right?
Not theoretically. On the NCO adjust, it still shows that it's trying to pull a frequency error.
Oh yeah, it was still about minus 35,000, wasn't it?
Yeah.
Yeah. So it's still kind of a bit of a mystery, but that we're getting 0-bit error rate, and getting it, fairly reliably and repeatably, I think is just really good news. So yeah, I think as Paul said, just more experiments. I have 2 things to still integrate that I haven't been able to get to. One is a lock detector circuit. And there's 2 benefits to the lock detector. One is that, we can have some hardware mechanism that tells us, yeah, the loops are locked or not, which I think could be helpful in this process. The other benefit from the lock detector would be that we could, and I don't think we want to do it yet, but we could switch from a set of acquisition gains to a set of tracking gains once we have lock. So that is remaining to be integrated. And then I also have another frequency compensation circuit that I need to review and see if it's useful, and we could try integrating that and see if that gives us any benefit as well. So those are still pending tasks, but I think we're still making excellent progress in the meantime. with what we're seeing in the lab today. So I thanks, Paul. I really appreciate the experiments you're running and seeing some good results from them. I don't think anything else for this.
Okay. Yeah, this is tremendous progress. And just in case we buried the lead here, we've had a lot of trouble getting over the air transmit receive like to work. And it looks like it's starting to work. So that's a pretty big milestone. We thought we had achieved it a couple of weeks ago. Unclear that that was real or not, but now we're starting to see some really promising results. And we also on the theory side, what we've been trying to do is document this in an article or paper to show the process of how you calculate the PI gains for a particular system. And this has had a lot of iterations, refining our understanding of the PI controller and how you get the gains. And gosh, why don't the gains that we come up with just magically work? So in the end, this will be a really good explanation, a design that works and an explanation. We've made some big steps forward. The process is messy and has lots of frayed ends, but we're tying them off and moving on. So it's been a really good week. So looking forward to the next week on that. And thank you everybody for all of this work. It's really delightful. Okay, so we have plenty to talk about on a project that we're working on. This is a Venus Earth. I hesitate to say communications, but it is sort of about communications. This is sort of a rate. How do you bounce signals off of Venus in order to get them back to the Earth so that you can receive them? And there's a whole a protocol and community and practice of bouncing signals off of the moon and using that as essentially a reflector or almost like a repeater for communications. And this is really cool. It's fun. Called EME. So when we want to extend that sort of understanding practice, and an operation to Venus or maybe some other planets too. And so we've been working on a link budget in coordination with the Deep Space Exploration Society, which originally reached out, invited us to a meeting, and it looked like, yeah, they needed a link budget and some analysis. And they redirected us to work with the Europeans. So we have, and it turns out there's a very enthusiastic community at Dwingeloo and also maybe some other sites. And one of our guests today is Thomas Telkamp, and he is at Dwingeloo. And I will turn the floor over to him to kind of introduce and describe and explain anything that he needs to talk about today. And then I'll hand it off to Pete, who has some specific feedback about the link budget. I'll go ahead and put the link budget up on the screen after Thomas has spoken.
Okay, thank you. I'll keep it short because I'm very interested to hear some of the other parts, so I don't want to waste all the time. So I focused on getting this test done today in Dwingeloo, where we bounce signals off the moon, also to get some experience and to test some things that might help us with Venus. The benefit we had today is that for part of the time, the Stockard telescope in Germany was also listening, so we coordinated that. And actually, I had the same tool set up in Stockard. So we had an IQ stream coming from Stockard to Dwingeloo. And then when we were bouncing off the moon, we could generate SIGMF files that have both the transmit and the receive in Dwingeloo as the receive in Stockard, all on the same timings and the same length and same start time, etc. So this is a really nice data set. I had something like 30 different waveforms. And it was all automated. So I could just bounce a whole directory of files off the moon and get all the results back. The other nice aspect today was that, so we have RHCP transmit and LHCP receive. Stockard actually has two linear polarizations on the receive only. So for Stockard, we actually have two files for every reception, one for horizontal, one for vertical, which means we can combine them again into circular, and then we can look for cross-polarization signals as well from the moon. So I think we created a unique data set. Pete, I also included your signal, so it worked. It went to the moon and back, and the file is there. I put everything online on the web. I will provide the URL. You can do what you want. It's all open data. But as I think this is a unique set, and we might publish something, please don't bypass me on publication without any coordination on this topic. This is quite unique, but happy to work with anybody. But please use the data for anything you want. And I've not caught up on all the interesting stuff on your Slack, but I will. And I saw a lot of interesting things, so I'll keep it at that and listen to the others.
That's super fantastic news about the success, and we'll study the results. And yes, we are we take to heart your request about publication and inclusion. That's what we live. So no, hopefully no worries there.
Oh no, that's why I already put it online.
I'll put up the link budget that we have, and kind of scroll through some of the new stuff. There's been quite a bit since last week. Matthew added a new mode, FS, I think it's FSTN. And then we worked on Doppler. I've done some very recent work on Doppler spread. And more. So we have some things in there. And then Pete also had some specific feedback about using Zadoff-Chu sequences, which are really cool. And we have some experience here with Zadoff-Chu sequences in our Neptune project. These are really neat sequences. They're totally cool mathematically. They let you synchronize. So what you're doing is you're figuring out your synchronization. This is spreading. Pete has some experience in CDMA spreading, spread spectrum. So what we're doing is really leveraging this to try to come up with a proposal for transmission for EVE that would really kind of cut through the loss because this path is pretty significant. So let me figure out how.
Can I add
sure, go ahead.
One quick thing, something I forgot. So yeah, I bounced a lot of these Zadoff-Chu sequences off the moon, also because I don't fully understand what the influence of the root is versus the echo, etc. So I just tried a lot of different values. But there actually is a communications protocol that is based on Zadoff-Chu sequences. I have a paper, and you might know it or not. I'm not sure. I mean, of course, I can share it with anybody, but I'm not sure if we should read it at this point because it's heavily patented, as far as I know. So we might be better off staying on our own track and figuring it out instead of being spoiled by what somebody else already has thought. But it's up to anybody.
Very well said. That is always a challenge that we do run into kind of a lot in what we do. Is that if we're dedicated to open source digital communications, and we all know that a lot of innovations and a lot of discoveries, inventions, practices, protocols, are covered by intellectual property, proprietary. So very good advice. So what we try to do is do our work from open sources, and also to be mindful that the regulatory relief that we have is that if we take advantage of the public domain carve-outs that we're in relatively solid ground. So yes, it's true. Zadoff-Chu sequence is a mathematical sequence that's very often used for synchronization pulses, very commonly encountered like in OFDM. They can also be used for communication, and you can actually do all sorts of different really fun things with them. They're not just for synchronization. In this particular case, in the link budget, what I did was say, okay, look, well, yes, the paper that we're reading combined communications with radar, which is a big area of research, especially in IEEE. And I was like, okay, we just want to get an answer back. We just want to see if we can get a signal. And so we're leveraging it mainly for ranging or synchronization. But it's true that you can use these for communications. And I think it was also Paul that brought up the fact that radar is not actually something that amateur bands can do. Radar is not one of the sort of approved modes. So there's some sensitivity here. Like it has to have some communications value. And then my counter argument is that there is actually some some relief here for the frequencies above 900 megahertz were allowed these pulsed modes. That's one of the reasons that we argue that we can do synthetic aperture radar on the amateur bands and experiment with it is because we're allowed these modes explicitly. So this is sort of it's a complicated subject, but we're using the Zadoff-Chu sequences. In this case, we're just looking at can you recover anything? Can you get any sort of signal back? And can you close the link? Now, can you communicate something? And the answer is yes. So that's not really reflected in the current link budget, but Thomas and others have raised excellent points. So I'm going to go ahead and try to share this. Okay, do you see what looks like a Jupyter notebook?
Yes, it's there.
Okay, good. All right. I know that's like a canonical question. You always have to ask, can you see the screen or can you see my slides? All right. So since last week, what we've done, we have an introduction and we compare EVE to EME since it's the closest thing. And then what I did is I put in a roadmap. So just to keep us kind of straight on all the things that we can do with this or should do, or, kind of keep it directed. Then there's a lot of different information here about development, potential community involvement, optimization, documentation, all the stuff that we care about. We've already checked off quite a few things along the way. So this is part of the document to kind of show our view on how this work should happen and some guidelines. We start off with the code part with the imports and the data class definition. We set up a data class for the site on the Earth. Right now, we only have DSES. I think that we really should add Dwingeloo and any other site that we think we might be able to use, like Stockard, maybe Bockham, maybe whoever else would like to be involved that we want
Green
to
Bank, maybe?
Yes. So that would be where, this data class section. A data class is a Python thing. It's a class that's just variables. So it's just values. It just stores the data. It's a class of data, and that's it. No methods, no verbs, just nouns. And in order to make this link budget flexible, then each data class, unfortunately, is going to have to provide at least some minimal set of the same information. So we've inadvertently blundered into an API here. So far we have DSES link parameters. These are things that are site specific. And I've also included things like the speed of light and stuff like that. That's not really site specific. So yet another data class might exist for things that are physically true. So, there's a never ending story of how to improve this. But, as of today, your data class represents things that are true for the site, regardless of the target. So your link budget today is EVE. The link budget tomorrow might be E Mercury E or E Mars E or something else, something maybe even terrestrial. So the data class is expanded a little bit since last time to include a few more things. And then we immediately go into a link budget class where all this does is it computes all of the gains and losses that we have for the link budget. And this is it as of today. We're fairly confident of this number. It produces this, I think it's a dictionary. This returns these, key value pairs of various things in the link budget. And we've sort of converged on getting the carrier to noise ratio in a 1 hertz bandwidth. And that's where the rest of this link budget will then pick up. So other parts of this link budget take that number, along with the things that are up here in the data class, the values from the specific site, and then do their work. So we set up a calculator. You have a class. We've defined the methods. Now we need to actually define the calculator, the object that actually does the work for us. And we hand it the parameters. So this is where you would link up your data class to your particular link budget. What we did is we just said, hey, Venus is different than the moon because it moves more. It gets much further away, much closer. Thomas's advice has been to really just look at it when it's closest to you. Don't worry about it when it's really far away, because that's like a 30 dB difference. It's pretty extreme out there. We have a pointing and tracking error worksheet to show you what it looks like when you have a pointing error or a tracking error. You actually can lose quite a bit with a big dish without a whole lot of pointing error. And we just take the number from the sites and say, okay, yes, this is the pointing error that you are reporting to us. And I did this again with tracking error normalized by beam width ratio. It didn't seem to give different results. So these probably will need to be combined at some point. We do a link budget at minimum and maximum distance. We get our carrier to noise ratio in 1 Hertz bandwidth. And then we start asking how much Doppler do we have? And I think this might be new since last week. So how much Doppler do we have? And I started out with this, like essentially from the center of the Earth, just to learn the Skyfield module or Skyfield library. But that doesn't really give you the full picture. You really have to be on the surface of the Earth because the Earth is rotating and adds Doppler, and it's significant additional. So I kept all of the old in here, but the from location methods are including the location on the Earth. And this took quite a bit of fiddling around with and testing. I think it's working. It seems to be consistent. Needs some review. Okay, so we have all these methods that do all sorts of different things, like calculating the worst case Doppler. The thing that we're most concerned about with, I think, is the rate of change of Doppler. And the rate of change of Doppler is the worst when Venus is the closest to us. The Doppler shift is actually the best when it's the closest to us, when it passes and it briefly passes through 0 Doppler shift, but the rate of change is actually the worst when it's the closest to us. This is a summary of all the results. And again, like review, improvement, welcome, encouraged, comment, critique, please. Here's some visualizations, and this is totally fun. Here's the Doppler shift. I'm going to scroll down briefly to show you what the time range is. This is the next 30 days. So along the bottom is the next 30 days. And here is the Doppler shift. You could see it's dropping because Venus is moving closer to us. So Doppler shift gets better, and it actually hits 0 like here and here and here. And then it starts going away from us. So, we have a Doppler shift. We can see it here. Each of these individual little whoopsie-doos are from the Earth's rotation. So wee. And then we have relative velocity. So I went ahead and graphed that in case it was necessary. This is the altitude, and you can see altitude of Venus at DSES is pretty darn good. It's at up to 60 degrees. And then here is the rate of change. I'm sorry that these graphs should really not be connected, like here and here along the tops, because it's not visible. I'm not really sure I'll clean that up as soon as I can. But along the bottom edge, that's the worst case rate of change of Doppler, and it happens at the date expected on the 22nd or the 23rd. I went ahead and set the location because setting location is an important function that took a while to kind of get right because you could set it once in Python, but not again. And there's a hack in there to make it reset every time. So I would really appreciate somebody looking at that and improving it. But I changed the location to London and then Sydney and got the expected results with the expected altitude azimuth, with the expected, when it was visible, how high it is. So I'm confident that works. Here's a view of what it looks like from the center of the Earth. You can see things are a lot smoother. So this is like, if you were at the center of the Earth, what does all this Doppler shift stuff look like? You can see the difference, versus being on the surface of the Earth when you have all this added velocity from our rotation. So that made me feel a little bit better. The next part is Doppler spread, and this is not in the repository yet because it's pretty new. What I wanted to talk about or show was Doppler spread, and this is the Doppler that we get because Venus is rotating on its axis relatively slowly, but it's still rotating. So part of Venus is coming towards you, part of Venus is receding. So your signal, when it bounces off of Venus, is spread out. And some modes, if the mode is narrower than the Doppler spread, then it's going to be affected completely by the Doppler spread. And if the Doppler spread is smaller compared to your mode bandwidth, then there's less damage. Right now, the center part, the Doppler penalty versus spread, is a simple model that does not kick in until the Doppler spread exceeds the bandwidth of the signal. We have a lot of active discussion about this. This is an attempt to kind of show why we should care about this. We need to mathematically prove it and improve this model. And so the question is, why does this matter? Well, it matters because in the mode analysis, when we take all of the modes that we know about, all of the amateur modes that we can collect, and once we get the proper understanding of the noise bandwidth, because I misunderstood, I thought the mode bandwidth was where the SNR was measured, but it's not. There's a lot of normalization in the amateur bands around 2500 hertz and not the bandwidth in the brochure. Once we kind of got that sorted out, then we got a good ordered list of which modes can close the link. And well, here's all the modes that we know of so far. The Q modes and the whisper modes and FT8, those are all the JT modes, from the JT suite, software program for weak signal work. We include CW, we include single sideband, FM, and RTTY, radio teletype, and PSK31. We include all those, and we'll include more. This table can get as large as we want, but we get through all these modes, and then I think Matthew can talk about the recent addition of the FST modes. So we have this table, and we know the required SNR. We know what the noise bandwidth is. Now we can take our results from our link budget, and we can say which one of these can close the link. So we have the ability to add new modes, evaluate the modes, which is what this does. We can filter by mode type, and we can get a feasible modes. And then we go ahead and look at the chart. So when we look at the chart, without considering the Doppler spread, the spreading or smearing of the signal because Venus is rotating and that's going to spread out our signal a little bit, we actually do have two marginal modes. There's an FST4W-1800 and FST4-1800. The rest are not feasible. They don't close the link. When we include Doppler spread, we're now 12 dB down. Again, this is a simple model of Doppler spread, so it deserves more scrutiny. But if there's any effect on Doppler spread, then these marginal modes here at barely above the noise floor here, they're not feasible. We can filter modes, so we show that we can filter out modes, so you can search for different modes. Feasible modes without considering the Doppler spread return these two. Results filtered for feasible modes, including Doppler spread, do not return anything at all. Okay, so those are the existing weak signal modes. Then we look at Zadoff-Chu transmission proposal. So this PDF was sent out yesterday. I was trying very hard to get in front of the 4th of March experiment at Dwingeloo, and to provide at least some reassurance that we're on the right track. And so this is just a little part of the write-up that I included in the link budget to kind of explain it, because there's not a broad appreciation for spreading codes or for, what does a chip mean, or, why does this work? What is processing gain? So this is an attempt to kind of include enough in here to where somebody reasonably adept with the normal sort of amateur digital modes could kind of get on board. And this could be dramatically improved. So this is the set of calculations for it, and it can do it. It looks like it can do it. So the basic idea here is to use a Zadoff-Chu sequence. The key here, the approach here was to say, looking at our Doppler rate of change, how fast is the Doppler change as Venus is whooshing by us and it has a rate of change. What's the longest integration time that we can tolerate at the worst case? And that is going to be the number of chips that we have for our integration. And working from there, how many of those do you now need to also integrate again in order to get above the noise floor? So that's what this particular section tries to kind of lay out. And I think at this point, I think that there were some really good comments about this particular approach and using the Zadoff-Chu from Pete. So I want to turn the floor over to him. Last thing I'll talk about is that we still have this, we have a system noise temperature worksheet. This is very important for the link budget. And we had an estimate of a noise temperature from DSES. It sounded a little high to me. And then our initial back of envelope calculations were even higher. And with Thomas' guidance on how big dishes usually can be evaluated, we got a better number. So our current number that we're actually using for all of this is 47.8 Kelvin for the TSYS for DSES. So that's where that number comes from. What we like to do is fold in the system noise temperature for the site into the data class. Like it has to come from somewhere. It has to be cited and calculated out or confirmed in some way, because this actually can make a big difference to all of this. It's one of the key things. But anyway, we have a worksheet or a cell for that. So that's the summary of the changes on this budget. And I am going to, I'm going to stop sharing, because I think that that Pete has some images or some visualizations and has a lot to share about this Zadoff-Chu attempt and sort of the way to kind of leverage it and to think about it, and possibly some corrections for some of the assumptions in this part of the budget.
Good question.
Oh, sure, go ahead.
Just so when we talk about the Zadoff-Chu, we're still going to be using one of the modulations. This is just the data that we're sending on the modulation, on the chosen modulation. Is that right, or am I missing something?
Is it? Yeah, this is so the way that I do this is it's an IQ sequence. And oh, go ahead.
So it's directly modulated then with the you're generating IQ sequences.
Yes.
Directly from the Zadoff-Chu.
Yes.
Okay.
Correct. That's how we do it on Neptune. And as far as I can tell from the paper, that's the same sort of deal. Okay, Pete, the floor is yours.
So the really good news, one of the big accomplishments this week was we found the bookends on the problem. And so I took the numbers from the paper draft that Michelle posted yesterday and put those into a table. I was wondering if Michelle or someone could share just the table that I posted to the Slack this morning. It was just after 6 a.m. Pacific time.
Yeah. Let me go get that.
Yeah, that'll make it really easy. I put it in a compact table, and so it'll only take a minute or two to go through it. But basically, the bookends are C over N naught, which is our carrier power to noise density. That's one bookend, and the other one's Doppler spread. So the principal challenge of Earth-Venus-Earth communications is we have a really weak signal, and the Doppler spread smears it all out. So what I did was I put these in a table, and I formulated this table in a general way. So this works with Zadoff-Chus. This would work with FSK. This is generalized across all orthogonal modulation schemes. And here we're really just looking at the ability to detect, did our signal come back? So like I said, the bookends are Doppler spread and C over N naught. From Michelle's link budget, we know our C over N naught's minus 8.65 dB. So you can see that in the first row of the table under T coherent times carrier to noise density. And I'll explain that in just a second, how that comes to fruition. But the important thing is down the left side of the table, it shows the Doppler spread assumption for a range of values we might encounter on Earth, Venus, Earth. And on the right side, it shows you to get the required or the desired detection SNR of 13 dB, how long does the transmission signal have to last? And the first thing you'll notice is these are in hours. So they're pretty long. So I'll walk you through the table just really quickly now to show how that's the big conclusion, but I'll show you how I got there. So if you start in the first row, if you assume a 1 Hertz Doppler spread, you can coherently integrate against an FSK tone or a Zadoff-Chu sequence, anything you like, for up to a second. And when you integrate for a second, that correlation naturally has a bandwidth of plus and minus a half hertz. So you can have up to a hertz of Doppler spread and it all still goes through the filter, and that's just fine. So then the next column takes that T coherent of a second and multiplies it by C over N naught in linear units and then plots them in, or puts it here in dB. So you can see for a second, that's a Hertz bandwidth. So it's just our C over N naught that Michelle has in the link budget. So minus 8.65. And then we want to get to 13 dB as the goal from Michelle's paper. And it turns out that non-coherent averaging doesn't follow 10 log n, it follows 5 log n for weak SNRs. So I need it to do about 21,000 non-coherent averages to get to 13 dB. And as a result, you can see what happens is if you take a 1 second integration, a matched filter, say a segment of a Zadoff-Chu that lasts a second, and you send that 21,000 times and then non-coherently combine each matched filter, correlation against the Zadoff-Chus that you're just repeating the same thing over and over and over again, you end up with it lasts 21,000 seconds, which I think is 5.8 hours. So then you can see it goes down the list, and the only thing changes on each row is if you have more Doppler spread, your maximum coherent integration time is less. So as a result, you get a lower energy to noise density in the, as you see as you go down the third column. The minus 8.65 becomes minus 11.66, and when Doppler spread goes to 2. But if you follow through that, then the outcome is pretty simple. It shows that if we really want 13 dB, like we have in the paper for detection SNR, the transmit signal has to be really long, and it could just be a tone, or it could be repeats of a Zadoff-Chu. That's all fine. And this analysis is true for any of those possibilities. So what I concluded is the bookends, we know what they are. They're C over N naught and they're Doppler spread, and they're really tight together. So I'm not completely sure whether we can pull this off or not, but those are the numbers I have. And that's probably all I'll say, and I'll just let there be questions or move on.
I think this is really interesting. One question, the 13. I mean, I agree that 13 dB SNR is definitely a detect, but isn't that a bit a high target for us?
Michelle, that was from your paper, so I'll ask, where did the 13 dB come from in the draft as a goal?
Yeah, the paper from Thomas said 13. They wanted 10 to 13. I just said 3 for my Doppler spread. And actually the most of the JPL work that I looked at, they were willing to, like, as soon as it got positive, they would start, declaring victory. But I picked 3. The paper was 10 to 13. And we'll just have to talk to more people or try it a couple of times and figure out, like, exactly what kind of margin. The paper assumed a 10 to 13 dB post-processing margin in order for the data to be useful, and they didn't really go into any more detail about that. And I picked a margin of 3. If you say 0, which, I mean, a math land or a very theoretical approach would say, all you got to do is get above 0. We all know that that's probably not good enough, but that would get you into the ballpark.
So the paper was radar. Maybe that was the reason. I mean, if you're building a radar, you don't want to have a lot of false detects.
Yeah, the engineering trade-off here is, Michelle, if you could drop that 3 dB, then our transmit signal duration goes down a factor of 4. If you can drop that 6 dB, it goes down a factor of 16. So
Yeah.
If we can relax that requirement, then it's still going to be very many minutes for a
Right.
symbol,
Yeah.
it sure looks like, but it won't be like, half a day or something.
Yeah,
That's good news.
I got a different number for the integration time required based on, like, because I started from the rate of change of Doppler. So that was the thing that I picked, the one thing that kind of, like, set all the rest of the assumptions. So a simple model, but I wanted to be totally clear about, like, where did this number came from. It's like, if you're going to correct for Doppler shift, the gross Doppler shift, you still have to deal with the change, the rate of change. What's the most you can tolerate? And I think it's 1.34 seconds, worst case. Like when Doppler rate of change goes down, which it does as it slides away from you, then you can adapt. You could actually have a system that just adapts to like, okay, and you know what? If you have a system that can track out dynamically, then none of this really matters much. But I wanted it to be something that almost any site could do. If your site can just correct for Doppler and then starts, doing a reception, starts receiving, starts recording things, and doesn't do anything more to it, then you can play too. So that's at least the basis for the numbers in the little write up and in the and what's currently in the link budget. And I think this is a higher bar, what you're talking about. And so I think we should just work really hard to kind of like figure out what's the model that we want to include in the link budget and how do we want to define it and to find any mistakes made, most likely by me along the way.
So there's one thing that's different between our two approaches. Here for non-coherent averages, I used 5 log 10, and I noticed in the draft paper you used 10 log 10. So that's going to make a dramatic difference between the two.
Yeah, I think that point's very well taken. Because I'm just using Mathland. This is it should go from 20 to 10. That makes sense. But like, okay, 5, if that comes out of practice and is real, then I go in and I put that back in, and the most practical repercussion of that is exactly what's on this table, is that the signal duration is, you're going to have to do it for a lot longer. You're going to have to do a lot more averages, non-coherent averages. I think that
right, because every 3dB drives you 4x longer, so that's painful.
Yes.
But I think it's true.
Yes, yeah, and that makes sense. I mean, when you look at DSN and the integration times that they're working with, I mean, then they're working with things that are much worse than what we are, and then sometimes not about the same. They do all sorts of different work at DSN, but you can sort of look at their results, and the 10 log base 10 is optimistic. That's like the ideal. So I think I probably have some Mathland, that's what I call it, ideal cases in there. And I'm happy to change it to 5 and then document it in there and say we're gonna derate it because at low SNR, this is the practical real traction that you're gonna get with non-coherent averages. I already talk about like this is assuming that a lot of things don't hurt your non-coherent averaging, but they really do. Like you can't just do this forever. You will asymptotically approach a limit of what you can do. It's not perfectly immune to things like Doppler or noise. So that's what I can do. I'll do that next.
What frequency have you assumed you're using?
Oh, go ahead, Mike.
I'm sorry, what frequency have you assumed in this calculation?
Let's see, this is all at 1296 megahertz. We know that we can also use 2304 megahertz next year. So this frequency is fixed right now at 1296.
Thank you.
Of course.
So I was going to suggest, if there's any assumptions here, we can, if we put the moon in place of Venus and see what comes out from the model, we ought to be able to compare that to real, moon bounces, right? So that we can use the moon and data, all the good data we have from moon bounce to validate everything that we have here, right?
Oh gosh, that's a really good idea. I think I could probably get a couple of people that have EME stations that are retired scientists to help out with this, and I'm pretty sure Thomas might be interested in this as well. It's a really good.
I mean, then we have data from him previously, and then the data that they'll be taking here in the next work that they're doing, right? I mean, all that ought to be applicable, I think, to an effort to validate our assumptions.
That's also kind of what I did today. So, for example, we sent a 30-second Zadoff-Chu transmission, which were all repeats of the same 1-second block. And one of the things to try is to actually do the incoherent averaging and see how that works out over time. It's only 30 seconds, but it might help us a little bit in figuring out how this works in practice.
Awesome. Okay. No, it sounds like the next week will be very illuminating in many ways. Now, we're a little bit over time, and so I want to be respectful of everyone's time. So is there any last questions or comments from anybody about this work or anything that we've talked about? Anything that we've missed or anything that you want to see more of? Okay, thank you so much, everyone. Well, you do ambitious work here, and we literally could not do it without you and all of the other people contributing on our Slack and mailing lists. We really, really appreciate it. We will do this again next week. And also a big thank you to IEEE. We cross-list this through the AES Society, through Information Theory Society and the Consumer Technology Society, and we've gotten a lot of good feedback there. And we'll continue to publish everything that we do and to work towards really good, solid citizen science on the amateur radio bands. All right, everybody. See you on Slack. And if you have any questions, please feel free to reach out at any time.